welcome to lesson 4.4 on conditional probability and independence. Today we're going to learn to find and interpret conditional probabilities using two-way tables. We're going to use the conditional probability formula to calculate probabilities, and we're going to determine whether two events are independent. One thing to note is that probability can change. Even though coins and dice don't have memories, probability can change if we know that some other event has occurred. Let's think about tossing a fair coin twice. The probability model here, which is the sample space along with the probability, is we could toss a head and then a head and then a tail and then a head, and a tail and then a tail. Since there are four options, each one of them has equal probability. It would be 1 out of 4 for each one. So there's a 1 in 4 chance of getting each one. So we've got our probability model. Suppose that the first toss lands tails. This is what we call the given. We are given that the first toss lands tails. This changes our probability model. The new probability model, given that the first toss lands tails, becomes just tails then heads or tails then tails. Notice my denominator for my equal probabilities has changed. Instead of having 4 options, I am only left with 2 options. This is an example of conditional probability. We are given the first option, so we know for sure that it cannot be heads then heads or heads then tails because we know that the first toss lands tails. If we use this in probability notation, we know that the probability of tails then tails, given that the first toss lands tails, is 1 out of 2. There's only 2 options. Tails then tails is just one of those. Let's do a little review of our two-way table that we did with the pierced ears and whether a student was male or female. So we're talking about 2 events. Event A is that the student is male. Event B is that the student has a pierced ear. The probability of A is the same thing as whether or not the student is male. There are a total of 90 males, so that's what goes on the top. That's the event that we're interested in, out of 178 total. So we do 90 divided by 178, and that gives us 0.506 for my probability. You try to find the probability of event B, the probability of somebody having pierced ears. Go ahead and find that now. You should have found the total people that have pierced ears. There were 19 male and 84 female for a total of 103 people having pierced ears out of 178. So it's 103 out of 178, which becomes 0.579. Now, the probability of A and B, we're looking at the intersection here. The intersection of being male and having pierced ears is right here. The probability of A and B becomes 19 out of 178. So 19 out of 178 is 0.106. Now, probability of A or B, some of you were really careful about using your formula last time. All we have to do is add our probability of A, which is 0.506, to our probability of B, and then I need to subtract the overlap, the probability of A and B, 0.106. So we're going to do 0.506 plus 0.579 and subtract 0.106, and that gives me 0.979. That's such a large number because there were only 4 people that weren't included in the probability of A or B. Remember, A was the student being male, B was the student having pierced ears. The probability of either being male or having pierced ears includes almost everybody but these 4 people. These 4 females who did not have pierced ears did not fit into that category. If we know that a randomly selected student has a pierced ear, what is the probability that the student is male? That is giving us something. There is something that we know. The given is that the student has a pierced ear. We know this for sure. It's a given. The word given changes our denominator. The probability of a student being male given that they have a pierced ear. So remember, we know for sure that they have a pierced ear. That means we can get rid of everything else but this. We know for sure that that's true. We want to find the probability that they're male, so we still put 19 on the top, but the given that changes our denominator. Instead of using 178, we are now using 103. So that becomes the probability that a student is male given that they have a pierced ear is 19 divided by 103, which is 0.184. Now let's look at this backwards. If we know that a randomly selected student is male, what is the probability that the student has a pierced ear? What are we being given here? We are being given that the student is male. We know that for sure. It says we know that a randomly selected student is male. So we are only looking at our male column here. We know for sure that the randomly selected student is male. What is our new denominator or our new total? You should have said 90. 90 is our new denominator. So the probability of having a pierced ear, given that they are male, well, right here, there are 19 students that have a pierced ear out of 90. So we are doing 19 out of 90, and that gives us 0.211. This is an example of conditional probability. The probability that one event happens, given that another event is known to have happened, is called conditional probability. And we have a new notation to go along with that. This line, this straight up and down line, which you can find on your keyboard underneath the backspace key, is the probability of B given A. It gives us a way to restate our previous answers. So instead of having to write out the probability of being male given that they had a pierced ear, we can change this given to this up and down bar here and change that to A and B, so it's the probability of A given that B. If we do this backwards, the probability that a student has a pierced ear given that they are male, we can change that word given to this up and down bar, so this becomes the probability of B given A. These notations are significantly shorter than having to write all of this out if you identify what A and B stand for at the beginning of your problem. There is a shortcut to calculating conditional probability. This is particularly helpful when we don't have a two-way table. If we want to look for the probability of A given B and we don't have our table to look at, we can just divide the probability of A and B divided by the probability of B. Let's talk about independence. Suppose you toss a fair coin twice. So your events are that the first toss is ahead, and event B is that the second toss is ahead. Remember, coins don't have a memory, so the probability of A is 1/2 and the probability of B is 1/2. So now, what if we use given that? Probability of B given A, the probability that the second toss is ahead given that the first toss is ahead. Remember, the coin has no memory. The probability doesn't change. The probability of B given A is the same thing as the probability of B. They're both 1/2. The probability of B given A complement, the probability that the second toss is ahead given that the first toss is not ahead. Remember that little C means complement, not. Again, the coin has no memory, so whether or not the second toss is ahead or the first toss is not ahead, the probability is 1/2. That never changes because coin tosses are what we call independent. A and B are what we call independent events. A and B are independent events if knowing whether or not one event has occurred does not change the probability that the other event will happen. Again, coins and dice have no memory. Whether or not I flipped a head on the first toss has nothing to do with what happens on the second toss. But that's not always true in life. So we have some formulas to help us calculate whether or not two things are independent. And these are actually two separate formulas that the book kind of squishes together here. Sorry about my messy boxes here. If we can find the probability of A given B, and that is equal to the probability of A given B complement, then we know that these are independent. If we switch this around, the probability of B given A is equal to the probability of B given A complement is equal to the probability of B. Again, if these two formulas are true, then we know that these items are independent. So this is a way to check for independence or to verify that things are not independent. Make sure you've written these formulas down before you move on. Let's go back to our ear piercing example. The events of interest were that A is male and that B, the student, has the pierced ear. We want to check whether these events are independent. Does being male have anything to do with whether or not you have a pierced ear? If they are independent, then the formula below will be true. So let's verify this. What we want to do is break this up into pieces, and we've talked about before being a lazy mathematician. I've already calculated the probability of somebody having a pierced ear given that they were male. That was the probability of B given A. We found that to be 19 out of 90, which is 0.211. What I've just found is this piece right here. The probability of B given A is 0.211. Now I want to check to see if it's equal to the probability of B given A complement. So the probability of B given A complement is the probability that a student has a pierced ear given that they are not male. We are being given something, so we need to change our denominator. We are given that they are not male, which means we are only looking at our female column. Now, I want to look at the probability that they have a pierced ear given that they are female. Well, there are 84 people with a pierced ear and 88 that are total female. So we do 84 divided by 88, which is 0.955. These two things are definitely not equal. I don't need to check anything else because the rule has already been violated. If these two things were equal, I would need to keep going. Knowing that the student is male greatly changes the probability that the student has a pierced ear. Since these are not equal, the rule has been violated. Being male and having a pierced ear are not independent. They are not independent. There's another way to determine whether events A and B are independent using the formula above. We can compare the probability of B given A to just the probability of B, or the probability of A given B to just the probability of A. That's these pieces of the equation. We can skip that middle portion if we would like to, if that's easier for us to do, and check the rule here. So let's calculate the probability of B given A again. That's the probability of having a pierced ear given that they are male. We've already looked at that before. There are 19 students that are male out of 90 that have 19 students that are male and have a pierced ear out of 90 total that are male. We've already done this before. That's 0.211. Now, what's the probability of just a student in general having a pierced ear? Notice that has nothing to do with male or female, and it doesn't say given that. So we are just looking at the total that have a pierced ear, that's 103. Out of the total students, it doesn't say given that, so there's no reason to change the denominator. So we do 103 divided by 178. And so that gives me 0.579. So are these independent? No, these are not independent. A and B are not independent because it violates the rule. Being male and having a pierced ear are not independent events. At this point, are you able to find and interpret conditional probabilities using two-way tables? Are you able to use the conditional probability formula to calculate probabilities? And are you able to determine whether two events are independent? Make sure you have your important formulas written down and be ready to use your notes in class today. See you.